This whole thing is a circle. 360 degrees, which is equally partitioned, right, as I look down that molecule. Because if I look down, right, as I'm holding it here, as I'm looking down, I have broken up this 360 degrees into 1, 2, 3, 4, 5, 6 equal angles. So every one of those angles is 60 degrees. Right? 360 divided by 6 is 60. But here's the weird thing. Normally, when we speak of angle, we talk about an angle where two objects are fixed at a single hinge point. A single hinge. So such an angle is referred to as a monohedral angle. Right? I have two objects that are connected to each other by one hinge point. Mono one, hedral for hinge. There's one hinge point. When I look down this molecule, it looks as if the angle between, for example, this Cl and that H is 60 degrees. It looks as if the angle between that Cl and that Cl is 180 degrees. But those are not connected by one hinge point, right? So the angle between, if you look at the model again, the angle between this Cl and that H, although it looks like 60 degrees, and it is, this Cl is not connected to this H, right? It's a chlorine connected by two hinge points to the H. So this is not the normal monohedral angle. There are two hinge points. So that's called a dihedral angle. Okay? So this angle, these angles are all referred to as dihedral angles, right? Those are all called dihedral angles. Right? They're all called dihedral angles. So what we're going to explore is what happens as we rotate about the carbon-carbon bond and as we change the dihedral angles between groups. So let's start with that species, and I'm going to rotate it so I'm going to go ahead and pick one. I'm going to keep the front carbon stationary, and I'm going to rotate the back carbon. And I can rotate it, clockwise or anti-clockwise, it doesn't really matter. So I'm going to keep the front carbon stationary, and I'm going to rotate the back carbon. Let's say we're going to go this way. We're going to go anti-clockwise. So I will hold the front carbon stationary, and I'm going to rotate the back carbon counterclockwise. And I'm going to do it in increments of 60 degrees. So here we are. Okay, here we are. And I'm going to rotate the back carbon 60 degrees. So we now do this. So I'm going to draw this structure. Well, in this conformer, when I view this, if I were to go in any direction, say clockwise or anti-clockwise, I will encounter substituents on the carbons that alternate. In other words, from my vantage point, chlorine on the front carbon, H on the back. H on the front carbon, chlorine on the back. H on the front carbon, H on the back. Chlorine on the front carbon. So as I go this way, I stagger the sequence in which I meet a front group and a back group. So this is called a staggered This is called a standard conformer. And staggered conformers basically will look like this. Right? That's a staggered conformer. Okay? Or you know, they could look like this. Oops. Right? This is just as appropriate for a staggered conformer. Right? So front, back, front, back, front, back. Front, back, front, back, front, back. These are staggered conformers. That's a general skeleton of a staggered conformer. Well, what happens when we rotate 60 degrees? Well, what's going to happen is that the group on the front will block the group on the back. Right? I mean, if I started off here, if I started off here and I rotate 60 degrees in either direction, the group, if you're watching dead on, the front group occludes the back group. In other words, the front group eclipses the back group. So I would call that an eclipsed conformer. So fundamentally, as far as we're concerned, we are dealing with two different subsets of conformers: staggered and eclipsed. Well, technically, if I look down an eclipsed conformer, I would see either this or this. Because the front group blocks the back group. The front group blocks the back group. Well, that's useless, right? I mean, it's not giving me enough information as to what's behind. So it doesn't profit me to look straight down the molecule when it is eclipsed, right? So if you look straight down the eclipsed molecule, this will block that, this will block that, this will block that. So what you want to do is to look at it with your head tilted slightly to the left or to the right. Because that way you can peek past the front group to see the back group. Right? And it doesn't matter whether your head is to the left or to the right, you'll be able to peek and see what's behind. So if I put my head this way, then what I'll see peeking behind here in an eclipse conformer is a group here, and a group here. So if I twist my head this way, I see that. And similarly, if I had, I'll pick this model, if I had put my head and turned it instead this way, I'll see the group peek behind, peek behind, peek behind. Peek from behind. Now, it's important to note something very important. It's important to note something important. Good God. The relative position of the groups must match. In other words, if I tilt my head this way, so going clockwise, the back group is just past the front group, then it must always be just past the front group, just past the front group. If I tilted my head the other way, right? So let's say I'm going to go anti-clockwise, then here the back group is just past the front, the back group is just past the front, the back group is just past the front. Or if I were going this way, the back group is just before the front, the back group is just before the front, the back group is just before the front. If you don't do that consistently, it means you've increased one of the bond angles and decreased another. Okay? So you want to be really careful in how you represent that. And it takes a lot of practice. And if you don't already have models, you should invest instead of models because they're actually quite useful. Okay, so these are my eclipsed conformers. So I'm going to take this structure and I'm going to rotate it. by 60 degrees. And I know I'm starting off with a staggered, so I know I'm going to alternate between staggered and eclipsed. I'm keeping the front carbon stationary, so I'm going to go ahead and do that. So the front carbon is stationary, front carbon is stationary, front carbon is stationary, front carbon is stationary, front carbon is stationary. Right, so I can go ahead and populate that. So if I'm going clockwise, I think that's what we decided. If I'm going to go clockwise, I'm going to move this up, and this CL ends up hidden behind the H. Not to worry, I'm going to cheat and tilt my head one way or the other. Just remember. So I'm going to put the CL here. So this is just before. So when I move this CL comes in that position. The H now goes behind the CL. The CL is just before, so the H has to be just before. And then when I do the rotation by 60 degrees, this H hides behind that H. And that's just before. Okay? I'm going to do another rotation of 60 degrees. If I do another 60 degrees, that H now moves here. So the H ends up here, that H ends up here, right? And that CL ends up here. Another 60 degrees. That CL ends up behind that one, and I'm going to peak. Let's peak this way instead. If I'm going to peak, so if I peak this way, yeah. So the CL ends up behind the other CL. Right? This H behind that H. So just past, just past. And this H behind that H. Just past, just past. Another 60 degrees, and that CL is now here. Right? This back H is straight down. This back H is straight up and to the left. Another 60 degrees, and that CL now hides behind that H. This H hides behind that H. And this H hides behind the CL. Another 60 degrees, and that CL comes back down here. Keeping the front carbon stationary again. So the CL comes back here. This H now is in this position. And this H is in that position. So if I start off with this is a 60 degree, then 60 degrees, then 60 degrees, then 60 degrees, then 60 degrees, then 60 degrees. So 1, 2, 3, 4, 5, 6 60 degrees is 360. If I go 360, I should end up where I started. Okay? Now, there are pet names given to some of these, well, there are pet names given to all of them, but we are interested in 3 pet names. When there are typically large groups, sometimes they're the same group, which are at a dihedral angle of 180 degrees, this is often referred to as the anti-conformer, because they are on opposite sides. They are on opposite sides of a single bond. Now, we can't call them trans, because unlike this species, because the dihedral angle here is exactly the same as the dihedral angle here. And while I can call this trans, and I can, because it's for an alkene, a compound with restricted rotation, I cannot call this trans, because I have free rotation. Trans is a label reserved for a configuration, where the three-dimensional arrangement is permanent. I cannot use trans for a conformation, which is an arrangement where the three-dimensional arrangement is not permanent. So while I can call alkenes trans, I would call species with free rotation anti. In a similar fashion, cis for alkenes, restricted rotation. When there is free rotation, but the dihedral angle is 0, I'll call that syn. So cis is the syn, what trans is the anti. So that's an anti-conformer. Well, we're not interested in a special name for this one. This one is called gauche. So when the dihedral angle between the groups under consideration and this, there's usually something about those groups that's interesting. Either they're the same atom, or there's some, or the big atoms, or whatever. There's usually some reason you're highlighting those. But when the dihedral angle between the groups under consideration is 60 degrees, it's called a gauche conformer. This one, where the groups under consideration are at a dihedral angle of 0, this is called the fully eclipsed conformer. This is called the fully eclipsed conformer. Now, that's an absolutely stupid name for it, because either you're eclipsed or you're not. And this is eclipsed, but so is that, and they're all eclipsed. But when the groups under consideration are the ones at a dihedral angle of 0, it's called the fully eclipsed. It's a stupid name for it, but it's the name that is used. It's a fully eclipsed conformer. Again, this one would be gauche, because the dihedral angle between the groups under consideration is 60 degrees. And then another 120, and we're back to our anti. Okay. Well, the question we're going to run into, which is the question organic chemists will ask themselves, is fine. So I've got a plethora of conformers. The ones we have drawn are the extreme versions. So here, there's 180 degrees between these, right? Well, before we go from here to here, and rotate this, well, let's put this way. So right now there's a 60 degree difference between this CL and that H. The dihedral angle is 60 degrees. There are a million conformers between this one and that one. So while this angle is 60 degrees, I'll have one where it's 59.99999, then 59.9998, blah 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 blah, and 58, 57.5552, and there's an infinite number between here and here. I'm not interested in those. I'm only interested in increments of 60 degrees. Right? 60 degrees from the anti to the eclipse, 60 degrees from this eclipse to the gauche, 60 degrees from the gauche to the fully eclipsed, 60 degrees from the fully eclipsed to the gauche, 60 degrees from the gauche to the eclipse, 60 degrees to the anti. I'm only interested in 60 degree increments. Otherwise, you can spend literally forever looking at them all. So that's point one. But what organic chemists are going to ask themselves to find? Okay, if we're going to settle on those 1, 2, 3, 4, 5, 6 conformers, because again, these are the same. My question is, what are their relative energies? You got 6 of them. Are they equivalent? What are the factors that affect the relative energetics of the individual conformers? Because that's going to become important. If you remember, we said that while we can rotate from that anti-conformer into this one, which is the fully eclipsed, it turns out that this conformer was more stable. Well, why is that? We need to understand what are the parameters that affect the relative energies of the individual species. So what we're going to do is lay some ground rules, which are entirely reasonable, and then we're going to plot this for a much simpler system. I'm going to plot it for a much simpler system. Oh, save us, Lord. Who's stable position? Okay, so what are our ground rules? What I might do. Okay, that's fine. That's fine. So what are our ground rules? Well, is there a fundamental difference between a staggered and an eclipse in terms of energies? Can we at least decide on that? Well, let's think. For now, I don't care what groups, if any, are on the carbons. And what typically causes repulsion anyway? Right? Well, what typically destabilizes a system, a chemical system anyway? And the answer is often is repulsion. Attraction stabilizes, repulsion destabilizes. Well, if I look at an eclipsed conformer, the electrons in the sigma bonds are close to each other in this eclipsed conformer, or closer to each other, than in a staggered conformer. This distance is larger, and if you get models, you'll see it pretty easily. Which means the repulsion between adjacent electron pairs on adjacent carbons, between electron pairs on adjacent carbons, is less, right? The repulsion between them is less in a staggered conformer where the distance is larger, right? And we talked about this at the very beginning. The force of interaction depends inversely on the square of the distance apart. The further apart we are, the larger the value of R, the smaller is the value of F. In a hurry, because R is squared. So the system in which the inter-electronic repulsion, or the inter-electronic distance, is large, means the inter-electronic repulsion is low. And when we minimize repulsion, we increase stability. So that's our ground rule. Our ground rule is the eclipsed conformers are more energetic than the staggered conformers. Ground rule. And in the simplest system, where we're dealing with ethane, where the groups are identical, all these are H's, in the simplest system then, we only have two options, staggered and eclipsed. And all the staggers and all the eclipsed are identical. So I'm going to go back now, and for this analysis, I'm going to replace all the CLs by H's, and I'm going to make ethane. So I'm going to replace all the CLs by H's. 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 Okay? Let's label the conformers as A, B, C, D, E, F, and A. And what I want to do is to plot a graph of the relative energies. So I'm going to have a graph of energy, let's call it enthalpy, against theta. And theta is the rotation, the number of degrees in which I've rotated. So I'm going to start here with A, 60 degrees to B, 60 more degrees to C, 60 more degrees to D, 60 more degrees to E, 60 degrees to F, 60 more degrees to A. Right? And again, these are 60-degree increments. Where's the energy of A? Well, I don't know. It's some non-zero value I don't know where it is, but it's somewhere here. And the value will depend upon the temperature and so on, but I don't care. It's some non-zero positive value. It's got an energy. But it's staggered. The eclipse, I know, is going to be of higher energy. So let's have the eclipse be at the energy value of that. Where's the energy of C? Well, A and C look pretty much alike. Now, they're not the same, because if I could somehow identify this H as being special, this H in A is now here in C. So they're equivalent, they're not the same. So the energy of A is the same as the energy of C. What about D? Well, D and B are also the same energy. Now, they're not the same energy as A and C, but B and D have the same energy as each other. So we say, for example, A and C, we can say they're either equi-energetic, or we can say they are degenerate, meaning they have the same energy. So the energy of D is the same as the energy of A. Not surprisingly, the energy of E is the same as the energy of C and A. You know where this is going? The energy of F is the same as the energy of D and B. And the energy of A is the same as the energy of A. So when I plot the graph of enthalpy against dihedral angle, I get a nice sort of sine wave looking thing. Okay. There is a delta H which governs the energy for rotation about that bond. That number, I don't know it offhand, that number is exceedingly small, which is why at room temperature, these things tumble at a million, it's not even a million, it's literally about 1,000,000,000,000 times per second. Because the energy to do it is very small, right? So to switch conformations, I mean, it's very, very small. Okay. Let's say I went from ethane to a slightly more complicated system. Let's make butane. If I asked you to do a conformational analysis which is what I just did here, it's an energetic profile of the various conformers going through a full rotation of 360 degrees. It's called a conformational analysis. If I ask you to do a conformational analysis of butane, well, you would tell me, sure, that's not a problem. Which bond am I looking along? Am I looking along the C1, C2 bond? Here? Because if I do, that profile looks very different from if I look along the C2, C3 bond. Right? That profile looks entirely different. So when we're dealing with something having 4 carbons or more, you're going to have to ask the question, which bond am I looking on? Because the C1, C2 bond, carbon 1, carbon 2, is very different from the C2, C3 bond. Now in propane, it doesn't matter, right? In propane, looking along this bond and that bond are exactly the same. But in butane, you're going to have differences. So let's go ahead and change now the H's to methyls. So I'm going to make this butane. Right? I'm going to change the H's to methyls. And And I'm just going to write methyls as Me, right? So front, and we're going this way. So this is the one on the back column. So it's methyl. And this is kept stationary. And that rotates, it's up here. 2 methyls are here. You're here because you're stationary. That's gauche. You're front. And now this methyl is here. And you're here and here. So let's go ahead and do a conformational analysis now of butane. Well, what does this look like? Well, what's the energy of conformer A? I don't know. It's some positive number. Oh, what I could have, well, this one. And if I were to superimpose the 2 plots, would the energy of the A in butane be the same as the energy of A in ethane? Let's think about it for a second. Which gets us to the other factors affecting the relative energies. Because we said our ground rule was staggereds are more stable than eclipsed. And when we're dealing with a symmetrical molecule like ethane, where all of the groups are exactly the same, all of the staggereds are the same. All of the eclipsed are different from the staggereds, but they're the same as each other. But clearly that's not the same here. And why not? Well, methyl, so H is a small atom. Methyl has a carbon and 3 H's. So methyl is a bigger atom. So when I had H on this side, these barely felt each other. Really, they didn't. They're tiny and at a dihedral angle, a separation of 60 degrees. They're barely aware of each other's existence. But when I make this group CH3, these feel each other. And what we now encounter is what's called a steric repulsion. And what does that mean? Steric is a term we use to describe the size and spatial arrangement of a group. And quite simply, if I have a big group, it exerts a greater steric force than a smaller group. So the other factor affecting the relative energies of conformers beyond staggereds and less